So in order to not to delay the agenda of the final of this final event, we have in the first place, Sylvia will, representing the European Commission, will give us some interesting insight about the upcoming policies impacting research and innovation. Then we will also have the opportunity to listen our project officer, Michael Schaffer, talking about the role of the Research Executive Agency. And then we will have the opportunity to listen all the CATCO2NVERS partners, starting with our project coordinator, Dulce from Funditec. And then we will continue with biorefinery approach, presenting by Perseo, Marcos Latorre. Then Mariana from Avantium will present the first of the 5 technologies, which is from CO2 to glyoxylic acid, and we will follow the presentation with the rest of the technologies. Last but not least, we will have the opportunity to listen to of our partners that are working as end users from Aviap and also Novamont that will be representing today. Then you will have the opportunity to have a Q&A section where you can enter any type of question. So as we expect to be this session very dynamic, feel free to enter any kind of question in the chat that is already available. And then we will have a very funny activity that I will give more details in the upcoming slides, but not now. And we will finish with a wrap-up and also a nice lunch for the people that is face-to-face here. So I don't want to steal more time. Sylvia, I think we could start with you. So feel free to share your screen.
Yes, good morning, everybody, and thank you for this invitation. And again, yeah. And so basically, good morning. So today, in fact, I'm very happy to be here because, in fact, first, I would like to listen to the outcomes from this project, as indeed the use of gaseous carbon to the production of sustainable feedstock is something that is gaining more and more, say, attention from many points of view. Can you hear me?
Yes, we can.
Yeah, all right. I think also that you saw the fact that even in the life sciences strategy that was adopted in July this year, there is a mention of the production of sustainable carbon for industrial uses from sustainable carbon from other sources than the virgin fossil sources, including the gaseous carbon. So say that basically you are in the picture of the future of the life sciences. But today I would like just to mention some of the elements of the new Horizon Europe framework program, because you may be interested as scientists and researchers in the new framework and the power of the new framework. So basically, the proposal from the Commission for the next framework program was adopted this July as well, and it was a part of the major package. Sorry, I don't know if I can change the slide myself. Apparently, yeah. So this is the a proposal from the Commission, which is part of the multi-annual financial framework that, in fact, will frame the splits of the expenditure in Europe for the next 7 years, starting from 2028. So the Horizon Europe framework program was proposed as a standalone program that will be the strategic tool to implement the innovation in Europe. but also it's partially, say, in synergy. It was presented in synergy with the European Competitiveness Fund, so that we will find a way to, say, support innovation in some key strategic areas. And perhaps the sustainable carbon and sustainable feedstock in general for industry in Europe can be part of that. So the legislative proposal basically it describe the framework, but also the rules of participation and the legislative financial statement in a way that, in fact, the first novelty indeed is the fact that there is a simplification going across all the pillar, in the sense that the program basically will be shorter and simpler, even in its specific program, because of course, according to the treaties, we will have the strategic part and the specific program for the implementation. And I said that there is also a possibility to have a synergy with the Competitiveness Fund. So to go straight to the power of these instruments, you see that in this proposal, Horizon Europe will be structured in 4 pillars. So not 3 pillars as the current one, which is in fact going to the end, because you know that we are about to adopt the work program for 26-27. So the next one, the proposal from the Commission is to structure the next one in 4 pillars, where you can see that there is excellent science, competitiveness and society, innovation, and European research area. So the novelty is that the European research area, will be a standalone pillar. So going to a broad view of the elements of these 4 pillars, you find that in pillar 1, you find more or less the same elements as usual. So the European Research Council, the Marie Sklodowska-Curie actions, and science for EU policies. That means basically the part that could be, in fact, covered by the JRC, the Joint Research Center for the Commission. Pillar 2 is the one, again, about both competitiveness and society, so tackling the part of the industrial competitiveness. And you see that there is a structure with 4, we'll say, elements that nowadays are the clusters. And with the biotech and bioeconomy, that maybe are the ones that are underpinning the subjects of today in the item number 2. And then we have other 3, say, challenges connected with the societal aspects. Pillar 3 innovation stays very similar to what it is today, with the European Innovation Council and the innovation ecosystems that will support, in fact, innovation. And finally, the European Research Area, where, in fact, the implementation of the Euro policies and the widening participation of all the countries, member states in Europe, in fact, will be pursued as objectives. So in the excellent science, we find a share of the budget of 44 billion. In pillar 2, we have a share of the budget of almost 76 billions, in fact, with a split that you see on the screen. And the item number 2, the one on biotech and bioeconomy, already with 19.7 billions allocated. And then we have the pillar 3 with 38.8 billions, and the European Research Area with an indicative budget of 16.2 billion. So basically, this is for me the aim of this very short presentation is indeed to make clear that there is an interest of Europe to invest in research and innovation. And this was made clear that it is needed through the Lecter report, Draghi report, the Heitor report. So all of these three, say, conceptual reports that inspired the proposals from the Commission, from the new MFF, in fact, stress the need to reinforce research, because basically it was assessed that from with €1 invested in research, in fact, the benefits, the revenue rises up to €11 in the EU area. So that's why I would like to give this message of optimistic message and positive message for the future that may be of some interest for you and inspiring you to understand what will be the follow-up of your research. And with that, I would like to stop and hear back from you if you have any question or comments.
Thank you so much, Silvia, for such a valuable presentation. I don't know if any of here or maybe in the chat has any question for Silvia. I don't think so. Let me quickly see the chat. No, I think that will be all. Thank you so much, Silvia, for your contribution. Since we are still figuring out the access to Michael, I think it will be a nice idea to start introducing the CATCO2NVERS project with our project coordinator, Dulce.
Yes. No sé si esto va. Voy a probar con este. No va, ¿no? No, si no, nada. ¿Le doy? Sí. ¿Le doy? Okay. Hello, good morning to everybody. Good morning to the people online. For me, it is a pleasure to be here to present the CATCO2NVERS project. Okay, so the project CATCO2NVERS is a European research project funded by under the work program of Horizon Europe, and it is a project that put together a team of 9 people working all together for more than 50 months, okay? And our general goal, it was to work together to reduce the industrial waste of CO2 and at the same time explore different possibilities and solutions to use this CO2 with different valorization technologies to produce biochemicals. This project started back in 2021 and it is finishing at the end of this month, okay, after, as I said, more than 50 months of hard work. Okay, so the general objective of CATCO2NVERS, it is to transform the waste CO2 that is produced from by 2 bio-based industries into 5 added value chemicals. And for this, we are using different technologies. The 5 chemicals that we chose are glyoxylic acid, lactic acid, furandic carboxylic methyl ester, cyclic carbonates, and biomethanol. And these chemicals are produced using 3 catalytic processes, biocatalysis, thermocatalysis, and electrocatalysis, in order to transform, as I said, this waste CO2. Okay, the team that has been working in this collaborative project, it is composed by participants from 7 European countries. We have 4 RTDs, okay, from Spain, Funditec, CATCO2NVERS, and CSIC. We have also Wageningen from the Netherlands, and we have 1 university, the University of Twente, 7 SMEs, okay, from Turkey, Poland, Germany, and Spain and United Kingdom, and 1 large enterprise. Okay, as I said, the general aim it is to use catalytic technologies. Catalytic technologies to convert the CO2 that is produced by these 2 bio-based industries that are using like lignocellulosic biomass, like Avantium, to obtain from the sugars glycols. They produce CO2, and also the other bio-based industry that is Perseo, that is a company that is transforming the organic municipal solid waste feedstocks into bioethanol, and in this production, they generate CO2 as a waste, and they also generate a waste stream like fatty acid methyl esters that are also a useful feedstock for other of the transformations that we take into account into CATCO2NVERS. This CO2, as I said, it is transformed from different catalytic technologies. Avantium is the leader of the technology number 1 that is based on electrocatalysis and produce glyoxylic acid. Then Wageningen University, it is working or has been working in developing a technology that will transform this CO2 through a biocatalytic technology, but biocatalytic method into lactic acid. On the other side, CSIC, the Spanish Research Center, has been working on the conversion of this CO2 to furan carboxylic methyl ester, that is a useful building block in the synthesis of polymers, and using thermocatalysis. The same process, the thermocatalysis, has been applied and developed by Funditec in order to convert this CO2 into another useful building blocks that are cyclic carbonates. And finally, another of the research centers, CATCO2NVERS in Spain, has been working to use this CO2 and also through another thermocatalytic process produce biomethanol. All these chemicals have, all this work has been also supported by companies like Johnson Matthey with expertise in the development of different type of catalysts. All these chemicals have a direct use in the industry, in different sectors or industrial sectors. For example, glyoxylic acid and lactic acid are being used as additives in the formulation of cosmetics. And this is why we have the support of companies like Evia. On the other side, lactic acid and furan carboxylic methyl ester, as I said, are building blocks and starting materials in order to obtain biopolymers that have been used in different applications, for example, by Novamont in the fabrication of biodegradable bioplastics. Also, as I said, these cyclic carbonates produced by Funditec from CO2 are building blocks to produce another type of polymers or resins, like the non-isocyanate polyurethanes that are sustainable alternatives to the traditional polyurethanes, and this has been developed in collaboration with Leda Polymers in Poland. And finally, CATCO2NVERS produce biomethanol, that it is a useful solvent that is part of the process of the extraction of useful materials for Perseo in their site. Okay. In addition to the technology developers, in CATCO2NVERS, we have the aim or the help also of ME20 that has been working very, very hard also in the downstream processes, okay, in order to find solutions for the treatment of each of the chemicals, okay. First, at the beginning of the process to try to obtain CO2 of better quality, okay, because these are catalytic processes, all of them, that are very that are depending obviously of the purity of the gas, okay, and also on the downstream process in order to obtain these chemicals that are coming from reactors and reactions to make them as pure as possible in order to be used in formulation of some delicate things like the creams, okay, in cosmetics. Also, we count with the help of an engineering company like EasyTech that has been the one that has worked on the development of prototypes that help us to reach a TRL 5 at the end of the project. So EasyTech has been working with us in the design and the improvement of the prototypes that have been able to process these chemicals in higher scale or higher TRL. Also, as part of the project, we count with the help of two companies, Nova Institute and Dana, that have been helping us, okay, on the sustainability and techno-economical assessment, a lot of work on this field, and in the communication and the dissemination, we count with sustainable innovation that has been helping us to organize events like today. Okay, so as I said, this is the summary. At the end, we work on 5 technologies, Avantium, Wageningen, CSIC, Funditec, and Cartif, in order to provide chemicals that we believe are useful in the chemical industry, in the polymers industry, and in other sectors, okay? Later on, we will have the opportunity to listen more details about each of the technologies. So I thank all of you for listening, for your attention, and obviously to the team of CATCO2NVERS for all the hard work that you have developed. It has been a pleasure to be with you 50 months together. Thank you.
Thank you so much, Dulce. So I think we can now jump to Marcos Latorre from Perseo Biotechnology, who will explain us the biorefinery approach that are carrying out actually in Valencia and also in Mariana's facility in Avantium. So go ahead.
Hello. Good morning. My name is Marcos Latorre. I'm the Innovation Manager of Perseo Biotechnology. Perseo is one of the 2 biorefineries that participate in CATCO2NVERS project. And I'm going to give a general overview of the role of biorefineries as suppliers of biogenic CO2, okay? So, well, most of you already know this, but I will remember this. Biorefineries are defined as the sustainable processing of biomass into a spectrum of marketable products and energy. So some key terms of this definition include sustainable. The system must deliver economic, environmental, and social benefits while minimizing negative impacts. And a spectrum of products. A biorefinery produces multiple products, both energy and non-energy related. Marketable. The products must have an actual or potential market with competitive prices. And the products can include food, feed, materials, chemicals, and besides the energy carriers such as biofuels, electricity, or heat. Okay. So biorefineries will play a key role in to achieve the goals of the European Green Deal to transform Europe's economy, and how they can contribute to these goals. Well, in the fossil resources replacement through the use of biomass as renewable sources of products and energy, for the circular economy and waste reduction by means of the valorization of bio-wastes into valuable products, climate action, reduction of CO2 emissions and carbon footprint, technological innovation. This will allow to develop innovative new technologies, and in the case of rural development, through the diversification of local economies and creation of new markets and job creation. So I'm going to describe briefly the two biorefineries participating in the project. Perseo Biotechnology is a Spanish SME focused on the development and implementation of processes for the valorization of organic wastes into advanced bioethanol, bioproducts, and bioenergy. We cover all stages of the valorization, from lab scale to industrial implementation. So this is how we work. We optimize the process at lab scale, then this perform a preliminary economic feasibility study, and if it's positive, then we go through the demonstration phase. And after a techno-economic analysis and LCA, if everything is positive, then we go to the process design and industrial project implementation. And to do this, we have our own patents, own labs, and a high capacity semi-industrial plant able to treat 25 tons of bio-waste per day. And we have large experience in engineering and in innovation projects. So here we can see the flow of valorization. We start from bio-wastes, which can come from different origin, and then after our submitting to our process, we can obtain advanced bioethanol. We can be used as a biofuel or as a chemical platform for the production of other chemicals, for example, bioethylene. And in this process, in this alcoholic fermentation, it is generated CO2, biogenic CO2, which can be valorized as it has been done in this project. We can opt also to produce advanced sugars, to produce a concentrated molasses of sugars, and this, in collaboration with other partners, can be used for producing other bio-based products. And depending on the origin, the byproduct of the process, which is called the vinasse, can be used for different, can be further valorized into biogas, fertilizers, animal feed, or even also extracting the fats and proteins from this biomass. And then we have also in the project Avantium as the second biorefinery, and the rate technology is a efficient process for the production of monoethylene glycol from plant-based sugars. And during this process, a side stream containing heavy polyols is inserted, and it generates green steam and CO2. So the waste CO2 and the ethylene glycol produced can be further electrochemically converted to glycolic acid, a process that has been developed within this project, as will be explained later. So the first step was to analyze the composition of the gas streams from both industries. In the case of Perseo, we, as would expect, we observed a typical composition from alcoholic fermentation with a high content of CO2 and some traces of other gases. In this case, what is particular is that we observe gases such as traces of methane and hydrogen sulfide, and this come from the natural fermentation from the biowaste during the storage, because as it was commented in the project, the feedstock was the organic fraction of municipal waste, and during this storage, some gases can be generated. And in the case of Avantium, the composition is typical from a combustion process with lower content of CO2 and nitrogen and other gases in low levels, such as CO or nitrogen oxides. So, of course, these gases cannot be used directly into the catalytic technologies, so they must be upgraded to purify them. And in this table, it is indicated the requirements that the partners in charge of this the catalytic technologies were set at the beginning of the project. But Wageningen and Cardiff had no specific requirements with regards to the CO2 level, but it required low levels of other impurities, while Avantium, CSIC, and Funditech indicated a high purity of CO2, higher than 99%, and low levels of the impurities. So, taking into account these requirements, what was done was to study the potential separation technologies, which were selected to upgrade these CO2 streams to be used in the catalytic reactions. Okay, and the results of the characterization were used as input for this separation process, and only processes considered at TRL higher than 6 were investigated, and using process simulation software, various scenarios using different separation technologies were investigated for the upgrading of the CO2. I'm not going to enter into detail in all the on the separation technologies. I will just give like show the final results. So for the CO2 coming from Perseo, the purification processes are include compression, washing, purifying, drying, and condensing. With these processes, it can be obtained a concentration higher than 99.9%. But in this case, we wanted to make in an economic balance. So it was defined this composition. And for the case of Avantium, the purification process was simulated in Aspen Plus, and based on absorption with amines as a mature method, and the purity increased from 95 to 99 by adding a water condenser. So, based on this, synthetic CO2 streams that avoid the impurities that were known to be toxic for the catalytic reactors, but allow some experimental testing with other impurities that are typical from these CO2 streams were provided, and it was assessed a good compromise between potentially harmful impurities and a realistic composition. And we proposed 3 mixtures for further validation of these impurities on the catalytic reaction. So basically, the idea was to evaluate the impact of some of these gases, some of these traces of gases on the catalyst lifetime and performance. So it was prepared like 3 mixtures to test the different traces of oxygen, nitrogen, and CO, and methane, and H2S. So to conclude, as I commented, biorefineries will be key to transform Europe economy and achieve Green Deal objectives. The production of chemicals from CO2 coming from biorefineries can make a significant contribution by solving 2 of the most urgent problems, which are climate change and depletion of fossil feedstocks. The composition of the CO2 gas streams generated by the fermentation and combustion process of the 2 biorefineries were analyzed, and then CO2 upgrading processes to the required degree of purity were evaluated, and mixtures compositions were established based on data obtained of the source, the technical specifications given by the partners, and the upgrading alternatives explored for these streams. And finally, we provided different synthetic mixtures mimicking these upgraded gases of the 2 bio-based industries to be validated in the project. All these activities were done in Work Package 1 of the project in collaboration with all the partners, and especially collaboration of Avantium, University of Twente, and Perseo. And that's it. Thank you for your attention. Thanks.
So now it's time to move to Mariana Paradiña from Avantium. I must ask you to be a little bit quicker, just a few more minutes, since we don't want to delay the break. If it's possible, I understand.
Just wait with me. I'm taking.
Okay, I'll let you know. Yes. We are a bit late, but not too much. Gracias.
Okay, yeah. Okay. Good morning, everyone. I'm Mariana from Avantium. I work as a scientist, and we were very pleased to join the CATCO2NVERS project. I think it was a great project, and I was very happy to work with all the partners. And at Avantium, this was a great opportunity for us to look at some sustainable ways of producing glyoxylic acid from CO2. Sorry. Okay. Just a brief introduction about Avantium in case you have not heard about this company. Avantium is based in the Netherlands, and the main goal is the development of sustainable processes and products from biomass. Very briefly, the company is divided in 3 departments. The most well-known is the Renewable Polymers division. Here, the focus is on the production of FDCA and PEF. And then I'm coming from the Volta team. And in Volta, our aim is to unlock CO2 as a new carbon source for the production of chemicals. And we do this via electrochemistry. Okay. And for those of you that are not familiar with electrochemical processes, why we do it with electrochemistry? Because it can be seen as a clean process. We use electrons as reagents, so we have less side products. It's flexible because we can adjust the production to the available energy at a certain moment in time. It's selective. We can prevent the over-oxidation and reduction of our reagents. And in terms of scale up, it can be seen as having a low risk because one electrochemical cell can be stacked in multiple cells, and then you can also have packs of cells. So we can de-risk the scale up of this technology. Okay, now focusing on the glyoxylic acid production. At industrial level, the glyoxylic acid production starts from acetaldehyde, which is a fossil-based chemical, and it involves the oxidation of the intermediates, and this means that it needs to use nitric acid, and it generates nitrous oxides. Alternatively, what we propose to do in CATCO2NVERS is the electrochemical reduction of CO2 to obtain glyoxylic acid, and this can be done in 2 steps. The first step is the direct conversion of CO2 into oxalate. Then there's an acidification step, and from there we can do the electrochemical reduction to glyoxylic acid. Here we have the overall concept in CATCO2NVERS. As Marcos explained, we have a CO2 source coming from the Dawn and Ray technologies, but the CO2 source can be a different one. In the case of CATCO2NVERS, this CO2 is converted into oxalic acid. And then in the second step, the oxalic acid reduction takes place in an aqueous environment. So we can pair this reaction with another reaction, and from there we can obtain 2 valuable products. In this case, we pair the oxalic acid reduction with ethylene glycol, and we convert ethylene glycol to glycolic acid. In CATCO2NVERS, we also collaborated with the University of Twente to develop a process for the separation and purification of glyoxylic acid, and then the obtained glyoxylic acid samples were tested in cosmetic formulations by EVIAP. Okay, focusing now a bit more on the work on the electrocatalyst development. Step 1, the CO2 reduction to oxalate. This reaction takes place in non-aqueous medium, and we make use of a sacrificial anode made of zinc for this reaction. And from the literature, the electrode that has the highest efficiency and also stability is a lead electrode. And one of the main goals in CATCO2NVERS was to find a replacement for lead electrodes, because we expect that there will be strict regulations with respect of the use of lead in industrial sites. So we wanted to look into alternative electrodes that could perform as good as lead for this electrochemical conversion. And then we also wanted to look at the impact of the impurities that we know that are still present in the CO2 streams after the purification, and see if these impurities would have an impact on the electrocatalytic performance of our electrodes. For the second step, here we also looked at the replacement of lead electrodes for the oxalic acid reduction, and then we looked at the integration of the 2 reactions in one electrochemical reactor. I don't have much time today, but I will just summarize the main results we obtained in the project. In the first phase of the project, we screened different electrode materials that had potential to achieve high efficiencies for this reaction. And then after we selected the most promising one, identified in that graph as CATCO2, we compared the activity of this electrode with the activity of lead. And we tested it in pure CO2, so that's the first bar. And then we compared the activity for the reaction in the same conditions, but using a CO2 mixture containing the contaminants. In this case, it was for nitrogen and CO. And the conclusion, as you can see, both for lead and for CATCO2, was that the activity of these electrodes is not impacted by the presence of these contaminants. We tested it also for mixture 2.1. In this case, it was for oxygen and methane. And again, for both electrodes, we didn't see a decrease in the activity for the production of oxalate. For the second electrochemical step, here you can see a picture of the setup we used in the lab for studying this reaction. First, we studied the single reduction reaction. And for this case, we had in the anode the oxygen evolution reaction. All the work was first done with this configuration, and then later on, we replaced the oxygen evolution reaction by the ethylene glycol oxidation. Here we have the results of some runs performed with a lead cathode that was represented in orange. So for lead, during 24 hours of runtime, we have very high efficiency towards glyoxylic acid, around 90, well, more than 95%. And then the first set of catalysts that we tested, I have one of here represented by CAT-N in green. The efficiency was considerably lower than what we obtained for lead, because we also produced a lot of glycolic acid as a side product. We screened a few more electrode materials that had the potential to be scaled up. And finally, we identified one here is CAT-I, and you can see that the performance was comparable to the one obtained with lead electrodes. In electrochemical processes, it's also important to look at the current density, because for industrial applications, we should target current densities that are higher than 100 milliamps per square centimeter to make sure that the production capacity is high enough. So the first studies that we have done, they were at 100 milliamps per square centimeter. That's our benchmark. But with Catalyst I, after these first tests, we also did some additional tests to see if we could increase the current density. And indeed, we observed that for current densities up to 200 milliamps per square centimeter, the Faraday efficiency was still above 95%. So this was a very good outcome. Okay, another important point is to look at the purification of the targeted products in CATCO2NVERS, and for that, ME20 was working quite hard on the purification of glyoxylic acid. In our electrochemical process, we start with an electrolyte solution that only contains oxalic acid. We don't need to use another supporting electrolyte, because oxalic acid also provides conductivity for the reaction. And we obtain a mixture of oxalic acid and glyoxylic acid. And what ME20 proposed to do was a separation process based on the different charge of oxalic acid and glyoxylic acid, and that can be done with electrodialysis. So having a first electrodialysis step, we can separate glyoxylic acid from oxalic acid, and we can obtain solution that has a purity of 95%. And then the other stream that contains a high concentration of oxalic acid, but also some glyoxylic acid, can be fed back to the electrochemical conversion step, and it can be mixed with the electrolyte solution. Alternatively, we can take that stream and do another purification step by electrodialysis, and here we can remove completely the glyoxylic acid from the oxalic acid stream and feed the pure oxalic acid back to the electrochemical cell. Now I would like to show some of the achievements that we reached in the second phase of the project, which was dedicated to the technology validation at TRL5. For this phase of the project, we collaborated with EasyTech. In a former project, we had built, together with EasyTech, a unit for the oxalate production. And in CATCO2NVERS, the idea was to upgrade this unit to optimize the reaction conditions, but also to change the electrode, because in this former project, we were using lead as a cathode, and we wanted to replace it. So in CATCO2NVERS, we have designed a new electrochemical cell that is highlighted there in yellow. And we went from 0.6 grams of oxalate per hour in the lab to a production of 180 grams of oxalate per hour in this unit. So that electrochemical reactor, the area of the electrode is 0.1 square meter. And in the lab, we are talking about small electrodes with an area of 5 square centimeter. And this unit is automated. We can do the filtration of the product that we have in the electrolyte solution. And as I said, this is a process that takes place in non-aqueous medium. So there was also a lot of work that had to be done in terms of safety, because we have to handle large volumes of an organic solution. We are handling acetonitrile, so we needed to make sure that the unit was safe enough to be operated. So we wanted to verify if we could achieve the same Faraday efficiencies. Oh, 3 minutes, okay. The same Faraday efficiencies as we had at lab scale. And in the past months, we were working really hard, and we were able to achieve efficiencies above 85% at 20 amps. So we were very, very happy with the results. Okay, I don't have much time, but just to show you also a little bit of the work that was done on the second electrochemical step. So also here we worked together with EasyTech on the development of an electrochemical cell that could be stacked for this reaction. This cell was smaller in terms of total area, but here we wanted to test the effect of stacking multiple electrochemical cells. We started from one cell that had an area of 25 square centimeter, and then the final reactor had included 4 cells, so we could increase the glyoxylic acid production to 25 grams per hour. Here is a picture of the setup that we also upgraded together with EasyTech in CATCO2NVERS. This unit is fully automated. We have been running it for more than 300 hours without any issues. We are very happy with the result. First, we tested the cell in a single cell configuration, and after overcoming some challenges, then we moved on to the stacked cells in bipolar configuration. Here we also did some studies, first only with the oxalic acid reduction reaction. Later on, we paired it with the ethylene glycol oxidation reaction. And so far, we were able to run the oxalic acid reduction reaction for more than 350 hours. And this was a great outcome because it allowed us to study also the stability of the electrodes. And just to finalize, we were able to find replacement for the lead electrodes for the conversion of CO2, but also for the conversion of oxalic acid into glyoxylic acid. The electrodes that were identified were we also needed to take into account that these would need to be materials that were easily scaled up, because one of the reactors for the design, it's important that you can have it assembled in the reactor. The impurities that we tested in the CO2 feedstock, they didn't show to have a significant impact on the electrocatalytic activity. And the reactions were validated at TRL5 in the units that we have upgraded together with EasyTech. For future projects, we think that it's important to look at the optimization and scale up of the paired electrolysis unit. And this should also include the integration of downstream processing steps, because in CATCO2NVERS, we only looked at the purification of glyoxylic acid, but we also have another valuable stream containing glycolic acid that we need to work on. And we should continue with the long-term stability tests when working with a stacked cell configuration. Thank you.
Okay, so now we should jump into the next technology, but we are gonna do like a quick break, a 20 minutes break. So see you all back at 10:25. For the people that is here, the coffee break will be, if I'm not wrong, in the terrace, right? 10:55, yes. I will put here the timing when we need to come back. So I hope you enjoyed the coffee. We are going to start with the next presentation, who is from Dan Van Vliet from Wageningen Food and Bio-Based Research. And he's going to explain us the second technology developing the CATCO2NVERS project, which is about from CO2 to lactic acid. So Dan, the floor is yours. Move the slide with this one.
Okay, thank you, Pablo. Yeah, so I will tell something about the technology that we developed in this project, which is a biocatalytic process from CO2 to lactic acid. Oh. Okay. So here you see the how a chemist would look at this process in terms of reactions. So we are looking at a system of 3 reactions that ideally would happen simultaneously. And these convert bioethanol, which you see on the left side, and CO2, which is in red, to lactic acid, which you see on the right. And that would then be partially consisting of this CO2. So the goal was to develop a 3-step biocatalytic cascade reaction. Another aim was to validate this technology by scaling it up to 0.5 liter and to reach 2 grams per liter of lactic acid or more. Also, we wanted to use industrial grade CO2 streams that were already presented by Marcos Latorre. And we wanted to demonstrate that with this lactic acid, you can make polylactic acid, PLA, which is a bio-based plastic, and in this case would be a partially bio-based, partially CO2-based plastic. And also, as you can see, there is an NADH regeneration system in this chemical cascade. And that this is a cofactor, as we call it, and this requires regeneration for the process to work. I will explain you later how we did that here, but we also tried to come up with innovative heterogeneous chemocatalytic solutions to accomplish this. No. Oh, sorry. Now the challenges for this is, first of all, nobody has demonstrated this, this chemical pathway with any meaningful product. And that is because the carboxylation step has poor thermodynamics. So it doesn't want to happen under normal conditions. Next to that, we are using a pyruvate decarboxylase enzyme to do this critical step. And in nature, this enzyme catalyzes the reverse reaction. So it is a challenge to make it catalyze the opposite reaction. And also ethanol and acetaldehyde that are used as the reagents here, they are not so great for enzymes and they tend to inactivate them. So that were our challenges. So how did we tackle this? First of all, we tried to find a good carboxylation biocatalyst because we knew from scientific literature that the ones that were out there were quite bad. But we did this by selecting a wide range of pyruvate decarboxylases from the databases. So you see here that we selected them from plants, bacteria, yeasts, and fungi. So that's a very wide diversity biologically. And we screened these in a reduced form of the reaction cascade system. So starting from acetaldehyde and using glucose dehydrogenase converting glucose to gluconate to regenerate the NADH cofactor. We calculated that this would be thermodynamically feasible. So therefore we overcome the thermodynamic barrier of the carboxylation reaction. And doing so, We found that 1 out of 31 enzymes that we screened in the end actually resulted in reproducible carboxylation. And this work was done at our partner Johnson Matthey. And we called this enzyme, this pyruvate decarboxylase, PDC20. This enzyme was characterized biochemically and also structurally. So here you see a crystal structure, as we call it, of the enzyme. It is a tetramer, and I will not go into the details of this, but this is very nice work. And of course, we wanted to see, does this enzyme work better if we optimize the reaction conditions? So going from very small screening scale to actual reactions in the pressurized reactor you see there, applying more CO2 pressure. That was the first thing that we tested, and indeed we demonstrated if you go from no CO2 pressure at all to 3 bars of CO2 pressure, the reaction works much better. You get about 2 millimolars of lactate formed from the 10 millimolars of acetaldehyde that we started with. But we also noticed there is a side product, and this is acetoin. And in the reaction scheme below, you can see that instead of combining an acetaldehyde and a CO2 to form pyruvic acid, which is the intermediate, this enzyme can also combine 2 acetaldehyde molecules and perform a carboligation reaction to produce acetoin. This is an unwanted product for us, so a byproduct. So another challenge here was to limit the formation of acetoin in our process. Now, how did we do this? We came up with the idea to use the molecule tris to form an adduct together with acetaldehyde, and in that way to keep the acetaldehyde availability low while keeping the overall acetaldehyde pool as high as before. And we chose to do this because we read in scientific literature from the 1980s already that this is a known process, that tris forms adducts together with acetaldehyde. We also analyzed what those adducts exactly were, and we tested it with our reaction, so adding different amounts of this tris molecule. And then we saw that indeed the lactate titer went up somewhat at 0.1 or 0.25 molars of tris, but more importantly, the acetoin product went down in concentration. And this is because the carboligation reaction forming acetoin is more sensitive to the acetaldehyde availability than the carboxylation reaction that are in competition with each other. So indeed, we confirmed our hypothesis and achieved a much higher selectivity by adding tris to the reaction mixture. Next, we optimized the CO2 pressure. So we tested out even higher pressures, up to 12 bars, and we found that indeed that leads to an improved reaction with more lactate and less acetoin, but it also starts to level off already from 5 bar onwards. That is actually quite favorable because, yeah, the less pressure you have to use for the process, the more mild the conditions are. And 5 bar is not that much. Next, we attempted to increase the titer because currently we achieved around 5 millimolars of titer with 50% yield, but that is quite low. So we wanted to investigate, can we perform a semi-fat batch kind of setup? So repeatedly dose reagents and see, can the system continue to make product to achieve a higher product concentration? And yes, we were able to do so. Up to 5 dosings of 10 millimolar acetaldehyde resulted in the end in almost 25 millimolars of product of lactate. And that is also matches the 2 grams per liter target that we set for this project. Now, if we zoom back to the original goal was to synthesize lactic acid from CO2 and bioethanol. And we have been working with acetaldehyde so far to simplify the reaction. We also did work on converting ethanol to acetaldehyde with biocatalysts, and we demonstrated that that works. I will not go into those results now. But we also needed to test, can we integrate these processes? So is it feasible to have a one-step process in which all these reactions occur simultaneously? Or are there discrepancies in the conditions that are optimal for these reactions that make a two-step process more ideal? And I've summarized the outcomes of this for you. So on the left, you see two variations of the one-step process, so the integrated reaction system. And on the right, you see the results of starting from acetaldehyde, either as a single dose reagent or with multiple doses. And then, yeah, you see that the yield and the titer are better if we use a two-step process, which is why, in the end, for the scale-up, we also decided to maintain this two-step process. That does not mean that the one-step process doesn't work. It does, but yeah, it is, with more reactions, it is just more tricky to optimize this system. And there are different optimal conditions for the different reactions. So we scaled up this reaction to a half a liter scale. We did this in a 2-liter pressurized reactor, which is basically a bigger version of the pressurized reactors we have been using so far. And we did this using an industrial grade CO2 mixture. So this also contained 10 ppm of nitrogen dioxide and 35 ppm of oxygen, which are some of the contaminants that were presented earlier that can be present in industrial grade CO2. And again, we repeatedly dosed acetaldehyde to attain a higher product concentration. And we used 250 milligrams of the PDC-20 biocatalyst for this process. And doing so, we achieved quite a good recreation of the previous results that we obtained at small scale. So we demonstrated that this process is quite scalable. Before we were at 47% yield, and now with a half a liter reaction we are at 42% yield. So we didn't lose that much performance here, which we were happy with. And we produced the 2 grams per liter that were targeted for this project. Now the product lactic acid is a chiral molecule. So that means there are 2 enantiomers. And for this project we actually aimed to produce L-lactic acid. But we found that the biocatalyst that we selected to do the last step in the reaction, so actually producing the lactic acid, with the best properties, was selective for D-lactic acid. So we ended up producing D-lactic acid instead, with a very high enantiomeric purity, more than 99%, which we were happy with. But we also then demonstrated later at smaller scale that we could produce L-lactic acid by selecting a different enzyme for the final step. At similar performance as we showed for D-lactic acid. Now we have a reaction mixture containing lactic acid, but also it contains acetoin, it contains still gluconate, because that is the product of the NADH regeneration step, and it contains a lot of buffer. So in collaboration with us, EMI Twente looked into how can we purify this, this product stream. And this comprised a combination of different purification techniques, so Donan dialysis, electrodialysis, nanofiltration, and reverse osmosis. So as you can see, this was a complex process that was proposed. I even simplified it here for this slide. And this was tested. The individual steps with synthetic reaction mixtures, not a real reaction mixture, worked quite well. But the complete downstream processing chain was quite challenging. And the reasons for this, the main reasons were that, yeah, there's a low lactic acid concentration relative to the other components currently. So this reaction would need to be optimized further in the lab before it is very meaningful to start optimizing the downstream processing. 2 grams per liter, we attained the target of this project, which is very nice, but is quite low if you look at industrially applied processes. And in turn, we discovered that the tris molecule, which was very nice for us that it increases the selectivity of this process, is not so nice to have in the downstream processing. For a number of reasons, it is difficult to separate selectively together with the other components, and it also degrades the membranes that were used in the process. So based on this, we learned some things that can also be used in further improvement of the reaction system to omit certain buffer compounds, for instance. Now, next, we wanted to demonstrate that with this lactic acid produced from CO2, we would be able to make polylactic acid, so PLA plastic. How to do this? It is a two-step procedure, which is already implemented in industry, consisting of first conversion of lactic acid to lactide, and then ring opening polymerization of this lactide producing the actual PLA. You see the reactions here on the right, and what that last step would look like in the lab is depicted here on the bottom. So performing the reaction and precipitating the product, and in the end you get left with a small amount of product. So the interesting thing here was that we had to, since we had a small amount of product from our process, we attempted to do this synthesis of PLA also at a small scale, which is challenging because at larger scale it is easier to control this polymerization reaction. And additionally, we tested whether these contaminants of the other products of the reaction, so that is gluconate and also the tris that was difficult to separate, would influence the synthesis of PLA. And you see this summarized in the table here, that first to make the lactide and to purify the lactide, was very possible if we start with only lactic acid. And we also demonstrated that we can make PLA from that with a good molecular weight, which is the most important property, so 121 kilograms per mole. But if we start adding the gluconate and the tris at a 10% ratio, so that is quite a big impurity, we also demonstrated that you can actually make lactide that has sufficient purity to make PLA from. So we were happy with that result. However, we also demonstrated if both of these impurities are present, so the gluconate and the tris, this is too much. The lactide becomes of low purity and needs to be purified repeatedly, which causes a loss of yield, so this is not ideal. However, one of the two impurities is tolerable. For the last bit, I want to tell you about the chemocatalytic NADH regeneration that we developed. So this is an alternative to the current process that we have been using, which is enzymatic, converting glucose to gluconate. But gluconate in this process is a side product. It would be more ideal to be able to use, for instance, green hydrogen as a reagent, since this would lead to only production of water or protons and therefore no byproduct formation. To do so, we investigated if we could use heterogeneous reusable metal catalysts for this purpose. And this has been attempted before, and the challenge here is to selectively produce the isomer that is required for enzymatic conversions, and that is the 1,4 NADH that you see here on the right, and to not produce the 1,2, 1,6 NADH or even the NAD dimer, which are byproducts from the chemocatalytic reaction. And you see the results here summarized in a table again. We investigated various catalysts for this purpose, and for two of the catalysts that we tested, which are highlighted, we found quite a high total yield, and we also found interesting selectivities compared to the ones that are now reported in literature. However, we did find that this yield is not near, and the selectivity is not near that of the enzymatic process we have been using so far, which is more than 99%. So we have improved this process, but these promising catalysts need further development to be actually interesting to apply for NADH regeneration, which is also why we didn't apply them for the upscaling in the current project. And on the right here, you see that we also did some characterization of these catalysts to show that the metals actually doing the catalysis are there. So to conclude, we discovered a novel carboxylation biocatalyst with very good properties, and that was characterized by Johnson Matthey. We attained the project aim of producing 2 grams per liter of lactic acid from industrial grade CO2 at half a liter scale. And we demonstrated that we could produce both D-lactic acid and L-lactic acid, both with very high selectivity, using 2 different lactate dehydrogenase biocatalysts. Now, the downstream processing was very challenging, mostly due to the low product titer. But we did demonstrate that, in theory, PLA synthesis is possible with a low level of expected impurities, meaning that the DSP for this process does not have to be perfect in the end. The metal catalysts that were developed for regenerating NADH with hydrogen were promising and were better than those reported in literature. And 2 scientific publications are underway to describe the biocatalytic process and the chemocatalytic process for NADH regeneration. So I want to highlight that this was, of course, not done by me. This was done by a team from 3 different project partners. And I want to thank them all for the nice collaboration and you for your attention.
Okay, so now it's time to jump to our project officer from the Research Executive Agency, Michael Schaffer. Michael, I don't know if you can turn your camera, unmute yourself and share your screen so we can...
Hello. Good morning. Can you hear me?
Yes, we can, and we can also see you.
Wonderful. So I'm sorry for the hiccups this morning. I had to pass by our IT help desk to get this sorted out, and yeah, finally we made it, and I'm connected. Sorry about the trouble in the beginning.
No problem, Michael. At the end, we were able to manage it. So I would like to introduce you. So Michael Schaffer has been our project officer since the beginning of the project. He is going to give us an overview about the role of the Research Executive Agency. It's part of one of the agencies of the European Commission. So Michael, the floor is yours. If you can try to share your screen.
I can share my screen, perfect. So I'll just do that. I have actually also prepared a little presentation which will help. Sharing. There is the share button. So here's the share button.
Okay, just let me know. I will start the present. Is it in presenter mode right now?
Now it seems it's loading. Now we can see it in full presentation, yes.
In full presentation, yes. Okay, thank you very much. So first of all, I would like to say a big thank you to the consortium, to all who have contributed to the CATCO2NVERS project, and with all your dedication and endurance over the past years when the project was running. I would also like specifically to say also a thank you for coordinator. I know the managers have changed over the time, but with all of them, big thank you to Oscar, to Madalena and Chiara for being, for us, the face of the project and being also super helpful and making also our work at REA an easy one. Let's put it that way. So the question is, yes, what's next? So first of all, I would also like to say I'm sorry that I cannot join in person. The reason for this is being, as maybe some of you are aware, that new proposals have been submitted and we are currently organizing the evaluations. And this is also means that with from the point of view CATCO2NVERS, a cycle is about to close. So you also had a successful proposal back then. The project, I mean, there's still 1 month left, but the project is now in its very final stage and the final review. So this all is maybe also like summing up what we do, but for you, you'll probably be interested. So what's next? So first of all, the wish is, of course, let's keep in touch. And we have some suggestions for you how you as a project and with your results can do that. So first of all, I'll just briefly like to point out that you have it is expected that you should pursue the dissemination exploitation efforts up to 4 years after the end of the action. And there are some tools out there that can help you and assist you in these activities. I just want to highlight this, the Horizon Results Booster, the Horizon Results Platform. For those of you that are still would like to publish, and maybe this can also extend over the after the project ends, to use the Open Research Europe platform, where beneficiaries from Horizon Europe and Horizon 2020 projects can use this publishing platform for your scientific papers, which includes an open peer review and article revision while being compliant with the requirements for open access and open science for these projects. What may be also of interest is that there is support on IPR management offered, and for this is the European IP help desk a contact person. I'll go a little bit in detail into the next few slides. And of course, apply to the Horizon Impact Award and get your project activities and outputs recognized and rewarded. So the Horizon Results Booster, I don't know if you see this, there's actually an info session upcoming Wednesday, 26th of November. In webinar form, and you can get help and questions on your portfolio dissemination, exploitation strategies, a business plan development, or even like to go for go-to-market strategies. Next would be, sorry, it's yes. So as to the support services on intellectual property, so there are some services including an Horizon IP scan. There are the help desk offers some e-learning pages. There is actually also a helpline, and also as a downloadable guidance on IP management available services that you can use. And the European Help Desk actually has some upcoming events to complete the portfolio on free of charge supports for European SMEs and beneficiaries of EU-funded research projects in the context of transnational business or EU and research and innovation programs. So like the next one is actually upcoming on the 9th of October and on the 13th. Feel free to check out the European IP Help Desk webpage and register for these events if this is of interest to you. They are, of course, as I said, free of charge. So this way. And of course, another way is to contribute is to public consultations. I'll just briefly mention there is, I think we have also sent this out, public consultations ongoing on the Circular Economy Act and on the Biotech Act. The consultation periods, they end in the first weeks of November, either 6th of November for the Circular Economy Act and the 10th of, November, the 10th of November for the Biotech Act. And there are also some information on these websites in case you are interested and would like to contribute. Sorry. This is, yes, and of course, apart from this, of course, you have now gathered yourself in your project in the consortium a lot of expertise, and we are also always looking for independent experts, not only from academia, but also private sectors, SMEs, innovation agencies, local or national authorities, to help us in the evaluation of new and hopefully exciting proposals, and also to have some opportunity to network with fellows. So we also have a webpage for the call of experts. So please feel free if you're interested and register, put in your CV some good keywords that will help us finding you when we will need you for the work as an expert. So, and of course, another way to stay in touch and to learn about these things, about these latest calls, please follow us on our social media pages, such as LinkedIn, Mastodon, EU Science on Instagram, and the EU Green Search on Twitter. And sorry. And that's it from my side. So thank you very much. And so I stop. Did I stop sharing? No, there I stop sharing. Okay.
Yes, thank you so much, Michael, for such a valuable presentation. I don't know if there are any comments or questions from the audience. If not, thank you again, Michael, for your participation. It's also very important to have the European Commission perspective, especially in a final event. So thank you so much.
And again, from my side, thank you very much again for your dedicated work, and also the results you are delivering. And I'm very excited to have the honor to follow your project, like not from the GAP stage. I was coming in a little bit later, but through these years, and it was also a pleasure to see how the project produced results and thrived. Thank you.
Thank you so much. Okay, time to move to the next presentation. It's time to our host, CSIC, Eva Maya, is going to present us the third technology, which is the third conversion technology about from CO2 to FAMA.
Hi, good morning. Okay, here we are. Okay, the objective of the CSIC in this project was the conversion of CO2 into furandimethyl carboxylic ester using furfural as a raw material, and by a thermocatalytic heterogeneous process. So probably the first question have in your mind is why we thought in this conversion when we prepared the proposal, and I am going to give you 5 good reasons, I hope, to convince you why it's interesting, this reaction. First, because we valorize CO2, which is a very hot topic nowadays. Second, because the monomer that we prepare is a very pursued monomer from the synthesis of polymers and plastics, as Patricio explained yesterday, especially because this is the monomer to prepare polyethylene furoate, which is a PEF, which is supposed to be or an alternative to PET. PET is the polyethylene terephthalate polymer, which is the current plastic used in the bottles and other receipts. So the idea is to replace this polymer that takes a long time for degradation by PIF. The fourth reason is because we are using as raw material, as I mentioned, furfural. Furfural is a very nice bio-based molecule, and it's an alternative to hydroxymethyl furfural, which is the molecule that actually is used in the industry to synthesize this monomer. However, the synthesis from this monomer is an oxidation and esterification reaction, and don't use CO2 as raw material. So we decide to use furfural, and because also 2-methylfurfural is a molecule that comes from glucose and takes the reaction to obtain 2-hydroxyfurfural is difficult. It's an hydrolysis, very difficult to do it. And the compound is very unstable because it depends on the temperature and the pH of the solution. However, you can obtain furfural more easily from biomass. And the fourth reason is because the process is an heterogeneous process. So we can use catalysts that we can recycle, and this is very nice for the green chemistry purpose. Okay. Well, how we did it? Well, we use this reactor, you can see in the slide, and the first thing is to introduce furfural inside the reactor and cesium carbonate as a strong salt, and a copper-based catalyst. We introduce oxygen at a pressure of 6 bar, and we heat the reaction over 80 degrees, more or less 6 hours. And then we release the oxygen and we introduce CO2. At the pressure of 10 bars, we heat for 200 degrees around 8 hours. In these conditions, we obtain this intermediate, which is a kind of organic dicesium salt, and without isolation of this intermediate, we remove the copper catalyst, we remove cesium sulfate, which we generate because we added some drops of sulfuric acid to liberate the salt. And then, after this catalyst was removed, we introduce the second one. The second one is a catalyst containing acid group, so it's a esterification, acid esterification using methanol as solvent. So the next question is, what kind of catalyst we made for this reaction? The catalysts belong to a family known as porous, hypercross-linked porous polymers that were a kind of materials that appeared in the scientific landscape around 2011 by the hand of Professor Bien Tan from Wuhan, who made this really nice polymerization using an aromatic monomer and an external cross-linker. You can grow a very nice network, 3D network, with a high CO2 uptake, which is the main application when these materials appear in the literature. So following this strategy, we prepare our catalyst. So the first one, a catalyst containing copper. To prepare this catalyst, we use this very nice monomer, very known in organic chemistry, which is a sulfene, because it has 2 nitrogens and 2 oxygen groups, which is very nice to anchor copper, and using a new strategy to prepare this polymer as an alternative to the solvent conventional procedure of Professor Bien Tan. We use mechanochemistry that allow the growth of the raw only using the energy generated by the collision between the monomers. So in only 1 hour, in a solvent-free reaction, we can prepare a very nice hypercross-linked polymer. So in the second step, we react this polymer network with copper acetate to incorporate the copper in the polymer. So we are able, during the project, to scale up the catalyst from 1 gram to 10 grams with this strategy. The second catalyst was prepared in the same way, in 2 steps. In the first step, using the mechanochemical polymerization, and in the second step, we introduce the acid groups into the network. And the same, we can scale also the catalyst. Okay, coming back to the reaction, we have defined the catalyst. I would like to resume or tell you some advantage and disadvantage of the technology we developed during these years. The first is a disadvantage because the intermediate is obtaining with moderate yield, 47%. But we have to take into account that this reaction is really difficult because the position 2 of the carbon 2 of furfural is a very unreactive position. So we need to force the conditions, and 10 bars of pressure is really low because most of the carboxylation in the literature are more than 40 bars, sorry. So this is a nice pressure to do the reaction. However, the second step, the acid esterification, is quantitative. So we obtain the monomer with high yield and high purity, which is very important. You can see here the nuclear magnetic resonance. We don't have impurities in this monomer. This is as we obtain from the reactor without any further purification. And also, as a proof of content of the purity, we made a polyester in the lab, not so nice as the Patricio. So yesterday, because our polymer was, our film was a little bit dark, but well, it's a proof of content that the monomer works in a polymerization reaction. Another advantage is the recyclability of the catalyst. You can see here the Cooper catalyst we can use in 5 consecutive runs without loss activity. And also another interesting point in this reaction is the second catalyst, because if we want to use the acid catalyst, we can use inside of the reactor, but we also can make the esterification outside of the reactor by using traditional or conventional ways for esterification, sulfuric acid or chlorhydric or even ambergris 15. Finally, I would like to mention that we also run the reaction using the 3 mixtures of gases, as Marcos explained before, and well, with the first mixture, which is the more pure, the process works pretty well. But with the other 2 mixers, we have problems because there are some impurities that poison our catalyst. In these 3 slides, I summarize, how we do it, about the catalyst, and all these results that I explained you briefly were summarized in this article that was yesterday accepted for publication. Well, during these years, we made hundreds of reactions, so it was a long trip. And during this trip, we prepare a lot of catalysts that doesn't work in the technology. But we decided to work in the parallel way and to rescue some of these catalysts to do another interesting conversions. For example, in the first year, we prepared this nice catalyst that has as active centers chloride imidazolium groups. And the catalyst works pretty well in the first oxidation reaction, but doesn't work in the carboxylation. Because the compounds at 200 degrees. So we decide to study in deep the oxidation reaction and compare with other soluble catalysts. And finally, we obtain this nice publication in Applied Catalysis A in the second year of the project. We also prepare another catalyst containing more chloride imidazolium groups, more stable catalyst, but doesn't work either in the carboxylation reaction, but was a very nice catalyst for the conversion of CO2 into formamides. And we also get a nice publication in Journal of Cell-Dose Utilization using this catalyst for this reaction. And these 2 catalysts containing these imidazolium chloride groups can be converted in new catalysts, a type of metal carbene catalyst, by reacting them with copper iodide. So we prepared 2 very nice metal catalysts that were very effective in the conversion also of CO2 into cyclid carbamates, which are this structure following different strategies. And this is the last work that we are going to publish in the framework of CATCO2NVERS, and it's going to be sent hopefully at the end of this month. Beside the copper catalyst I showed you before, we prepare another catalyst with other metals. For example, with cobalt, very similar, but with cobalt inside. This catalyst doesn't work in the reaction, but works pretty well in the carboxylation of another bio-based molecule, 2-methylfuroate. And we also publish this result in RC Sustainability. And during the, I don't remember well, but during the second or third year of the project, we tried to replace cesium carbonate by an heterogeneous super basic catalyst. We prepare a very nice catalyst, but doesn't work. We can replace cesium carbonate, but it was a very nice catalyst because we use for the production of biodiesel. So we use different oils coming from commercial oils or cooking oils, and made an esterification reaction with this catalyst and works pretty well in the synthesis of biodiesel. So we published also these results the last year. And, oh, sorry. No, but it's the same. No, siguiente, there's one. Lo estoy dando. Oh. Okay. All this work that I presented before regarding the use of this catalyst for the conversion was the content of the thesis of the doctoral thesis of Beatriz, which was defended the last July in the framework of this project. Okay. Yes, this is the conclusions of this technology. The first one is that we made the synthesis of furan and dimethyl carboxylic ester from CO2 and furfural, and this is able to prepare polyesters. The second conclusion is that we obtain moderate yield in the intermediate, but we develop very interesting heterogeneous catalysts using mechanochemical polymerization. We demonstrate also the recyclability of the catalyst, and we can make the acid esterification, the second step, inside or outside of the reactor. And finally, the technology can be done with simulate CO2 bio-based streams, but free of impurities such as hydrogen sulfide or nitrogen monoxide. Regarding the rescue of the catalyst that doesn't work for the technology 3, we say that we save at least three catalysts, and that generates interesting results and interesting papers. And of course, the thesis of Beatriz. So, what's the next? Well, as I explained yesterday, we have to scale up the procedure in the reactor built by EasyTech, and Funditech finished its valorization, and it's our turn. So, I hope that during this month we can scale up the technology, hopefully, and also we are working in the preparation of 2 grams, where we deliver 1 gram to Novamont. He showed you yesterday the nice polyester, and we are working also in the 2nd gram to deliver them. And finally, thank you. This is the CSIC work team, and I would like to say thank you to Elizabeth, who was working 3 years with me, and Elizabeth, and Beatriz, who stay all the time with me, and of course, Marta, senior support of this project. I am very glad to stay. Sorry. Well, and finally, the whole consortium, because I was very happy. Thank you.
Okay, so next technology is Funditech again. So we are gonna understand a little bit more about from CO2 to CCFAME. Difficult.
Thank you. Vale, no quieres que use este. Vale. Okay. Hello to everybody. Okay. Okay. The work of Funditech in CATCO2NVERS was mainly focused on develop a technology that is thermocatalytic conversion of this CO2 to cyclic carbonates that, as I said before, they are platform chemicals and building blocks for the synthesis of polyurethane resins. Our approach basically tries to accomplish four principles of the green chemistry. There are the atom economy, the use of renewable feedstocks, and also reduce the derivatives and use catalyst. Okay, so we have as a general objective to perform a one-pot, two-step process that goes from the valorization of some feedstocks on some valuable chemicals, vegetable oils and lipids that are present in agricultural waste, okay? And also to take advantage of the CO2 as a building block, as a chemical, okay? And valorize this. And the final idea is to obtain these cyclic carbonates. The overall process will be a one-pot, two steps altogether, but we first have a study, the first step, that is the conversion of these vegetable oils that contain alkenes in the structure to carry out an oxidation reaction to obtain epoxides that are intermediates, and then with the CO2 to perform the carbonation reaction and to obtain the cyclic carbonates, okay? These, as I said, are value chemicals. How is our approach? Our approach is based on a thermocatalysis, and for this, because of the nature of the CO2, that is not an easy, it's a tough molecule as reactive, we need the help of catalysts, okay? The value of this type of chemicals and catalysts that we have chosen, the porous organic polymer catalysts, is that they are easy tanning, okay, because playing with the chemistry, we can develop different chemical structures that hopefully will have enhanced affinity to the CO2. They have also a porosity, okay, and allow us also to post-functionalization, okay? That is, for example, to introduce metal sites to perform the conversion reaction. Okay, so our porous organic polymer catalyst, the synthesis, the first approach is the synthesis of these chemical structures that are supports, okay? These allow us to control the crystallinity and the porosity, and as I said, the tuning of the chemical structure will help us to enhance the affinity to for the CO2, and in a second step, it will be the post-functionalization with the metals, okay? For the synthesis of the catalyst, we started with a traditional solvothermal synthesis process, okay, using dioxane and in 100 degrees, 3 hours, and then we have explored another alternatives that are more sustainable. For example, the use of microwave synthesis, where, as you see, we can reduce the reaction times, okay, and it's an easy process, okay, that let us to obtain the catalyst that we need for this technology. In addition, and in collaboration with CSIC, we have also explored a later technology that is mechanochemical for the synthesis of this catalyst. In this case, we have proved also this methodology. We have obtained the same type of catalyst, of supports, okay, with no use of solvents and reducing the timing of the reaction, which is really an advantage. Okay, so these porous organic polymers that are the supports of our catalysts have been characterized. They have some features like high thermal stability, high porosity with surface areas around 200 square meters per gram. They have shown a good interaction with the CO2, that is our intention, okay, and they presented COF-like structures. So after the synthesis, the next step is the post-functionalization with metals. For this, we have reviewed the possibilities and the metals that we have in the periodic table, and we have chosen iron and cobalto, okay, because of the abundancy, they are abundant elements, and they have limited toxicity, okay. So after this introduction of the metals, we prepare our organic frameworks, okay? And the average metal content of each of these frameworks is between 1 and 3% weight, okay? So when we prepare a wide range of catalysts, okay, with different chemical structures, and we have analyzed all of them first for the second step, okay, that is the conversion of the epoxides to the cyclic carbonates. We have tested different conditions like temperature, pressure, amount of catalysts, different type of catalysts and co-catalysts, and different substrates, going from small molecules like styrene oxide, very simple one, moving to methyl oleate epoxide, that is already a derivative that comes from natural feedstocks, and then up to the epoxide soybean oil, that is more complex molecule, okay, but it has very much advantage because it's a natural derivative that is present in the vegetable oils. Okay, so after screening all these conditions and after screening a lot of catalysts, we selected one catalyst, okay, and with these ones, the best results conditions are a temperature of 120 degrees, 16 hours, and a pressure of 7 bars. That compared to the literature is quite an advantage, okay. The choice of this type of catalyst, it is, as I said, for chemical and structural reasons, but also because they are heterogeneous catalysts. And the advantage of this is that they have the possibility to be recycled and reused several times. So within the frame of the project, we have also demonstrated the recyclability up to 5 cycles, maintaining the high conversions and high yield, okay? The results of up to this development have already been published, okay, in a journal of CO2 utilization. Okay, as I said, the final goal or the overall goal was to perform a one-pot, two-step process. So for this one, this is the overall process. In the first step, okay, we found some conditions that are following the Mukayama conditions, and here we have found that it is necessary as a key conditions to use dry acetonitrile in this first step, because this enhances the solubility of the oxygen in the reaction media, okay, and that water spoils the reaction performance. Okay, so the first step, these are the conditions using a catalyst. This one of the catalysts we developed that is using iron as the coordination metal. Okay, we tested with small molecules like methyl oleate and also with the soybean oil. Okay, the soybean oil that contains this alkene structure and is oxidized to the epoxide using 3 bars of pressure at 80 degrees for 3 hours. And here it is necessary under the Mukayama conditions to use isobutyric aldehyde, that is a sacrificial agent, okay? But the oxidation reaction performs very well. Then we have also explored the second step, as I said, with the conditions here. We know that the isobutyl aldehydes and the derivatives cannot be present in the second step, so they need to be removed, okay? They are produced in the first step, the oxidation, and we have tested and found that they need to be removed. But for the second step, the conditions at low scale, we are talking about lab scale at this case, keep the same, 7 bars and 120 degrees. So after testing the individual conditions, then we tested the one-pot, two-step, so everything all in a row. So for this one, we have demonstrated the overall yields go down a bit, but still, even for molecules that are complex, like the soybean oil, the carbonate, it is obtained in a 60 overall yield, which is quite well, good result. So We perform this in a small scale, but in order to be able to test the final conditions with the prototype developed by EasyTech, we went step by step, okay? Elizabeth was testing conditions, okay, from the 10 milliliters up to 120 milliliters, okay, playing with the conditions, with the pressure, okay? And this was performed in another reactor that we have in the lab, a half-a-liter reactor, before moving to the final prototype, okay? So with this unit developed by EasyTech, also we were trying different conditions of the temperature, of the pressure, and here we, we managed to perform the reaction with up to 200 milliliters of the epoxidized soybean oil, using acetonitrile and 120 degrees of temperature. And in this case, in order to achieve these very high conversions, it is true that we need to increase the pressure of the reactor up to 20 bars. Okay. So out of this work, during these last weeks, we've been, when Elizabeth has been working on preparing quantities of this carbonated soybean oil. The good news about this is that we have a control system, a control reaction and technology, okay? And that with this technology, we are able to uptake up to 4 moles of CO2 per mole of the epoxidized soybean oil. So this really demonstrates the valorization and of the CO2, okay? And these materials have been sent to Leda Polymers, okay? That is our partner in charge of using this carbonated soybean oil in the synthesis of sustainable polyurethanes, like the non-isocyanate polyurethanes foams, okay? They are working already with this material, but in addition, this cyclic carbonate, okay, has been used by Funditech, okay, in the synthesis of nipus, and they have been demonstrated the value as adhesives, for example, in the preparation of boot sheet boards from this NIPO. So they have a value and they have a demonstrated utility in the synthesis of adhesives and also in the synthesis, I hope, of foams. Okay. So I want to thank all of you for your attention, but of course, my colleagues, not only from the Department of Management, but also the people that has been working in and doing this job, okay? That has been Marcelo Echeverri, is not here today, and Elizabeth Rangel, and another people in the lab that has been collaborating also in the production of the epoxide. So thank you very much.
Okay, time to explain the last of our technologies from CO2 to bioethanol. That is going to be presented by David Diez from CATCO2NVERS.
Hello, my name is David Diez, and I'm going to talk about the production of biomethanol from CO2 developed by CATCO2NVERS within a CATCO2NVERS project. First of all, I'm trying to introduce very briefly CATCO2NVERS. CATCO2NVERS is a technology center that is located in Valladolid, whose my mission is to try to help the companies to develop or produce new process and products. The center has more than 30 years of experience, and we are organized in 3 main technological divisions: energy, agri-food and process, and industrial and digital systems. We have more than 250 employees that are working in more than 150 active projects in this moment. Now regarding to the synthesis of biomethanol from CO2, as you know, this reaction is an exothermic reaction, so it's possible that hotspots can produce along the reaction and can generate the activation of the catalyst. Another problem is that this reaction is favored at high pressure. That means that it implies a higher production cost. And another problem is that we have a lot of side reactions that can reduce the methanol selectivity due to the presence of another byproducts in the process. So, taking into account all these drawbacks, the main objective of the CATCO2NVERS projects regarding to the production of the biomethanol is to develop a cost-effective catalyst that can operate at low pressure and temperature to try to avoid hot spots and try to achieve a good conversion and selectivity of the global process. To do this objective, along these tasks, we divide this strategy in 3 steps. The main steps were focused in the synthesis of the catalyst. This catalyst is basically made by aluminum fibers and hydroxide. The second step was a focus in the validation of the methanol using a prototype in which we introduce a separation unit and a recirculation system to try to increase the conversion of the CO2 in the process. And the last step was to try to produce a suitable amount of methanol to try to validate it as a solvent, task that was performed by Perseo. All of these objectives were carried out in collaboration with our partners, Johnson Matthey, Hysitex, and Perseo, of course. In this slide, we try to summarize the 3 key points of our catalyst. First of all, we try to use aluminum fibers with the objective to try to get an homogeneous temperature along the bed and try to avoid the formation of hot spots. Also, we use copper and zinc as active metal and promoter to produce methanol at a moderate temperature and pressure. And also, we use hydroxide to try to increase the partial pressure of the CO2 in the surroundings of the active metal in the catalyst. With all of these aspects, we try to avoid the hot spots and increase the CO2 concentration to try to increase the conversion and the selectivity of the process. So, to that, one important element in our catalyst is the synthesis of multimetallic catalyst supporting aluminum microfibers. This catalyst is made using commercial aluminum wool. First of all, we simply cut weight and place this wool in a different set of discs with an internal diameter of 10 millimeters, and then we apply different pressures with the objective to obtain our aluminum sheet supports with different grade of porosity. When we have already these supports, the next step were trade the surface of these fibers by different thermal and chemical oxidation with the objective to prepare the surface of the catalyst until the next step. The following step was the impregnation of the surface of the catalyst with the copper and zinc metals that are our interest metals in this reaction, and then dry and calcinate the final catalyst. So in that we, at the final, we obtain our copper and zinc catalyst over the aluminum fibers. Another element of our catalyst is the synthesis of the magnesium aluminum hydroxide. In this case, we use two solutions, one solution that contains the magnesium aluminum nitrates and another solution that contains the carbonate and hydroxide sodium solution. The objective is to try to co-precipitate the catalyst, the hydroxide, at a constant pH. The slurry that we achieved in this process was then aging at a constant air flux overnight, and then washing and filtering several times, and finally drying and calcination. At the final of all of this process, we obtain our magnesium aluminum hydroxide. This hydroxide was then well mixed with our previous copper and zinc aluminum fibers in order to obtain our final catalyst. Okay, in order to produce our final product, we follow an interactive process. So we start with a synthesis of one catalyst, trying to fix the several variables of the process of the synthesis, then characterize the catalyst by different techniques, and then evaluate the performance of this catalyst by activity test. In some cases, also, we analyze the spent catalyst in order to try to know how was the performance of the catalyst along the reaction. With all of this information that we can collect along this process, we go to the first step to try to synthesize a new catalyst to improve our product until we get a suitable catalyst that we consider that is suitable for our purpose. One important step in this process is the activity test. To carry out this process, we use a fixed bed reactor with an internal diameter of 10 millimeters. This system has also at the outlet of the reactor two chromatographs with the objective to analyze not only the products that we are generating along the reaction, but also the main reactants that are not reacted at the final of the process, mainly hydrogen and CO2. A typical process consists basically in to introduce a small amount of the catalyst inside the reactor, then activate the catalyst using hydrogen in this case, and then to run the different reactions to obtain methanol, modifying the variables that we are studying in each moment. Performing this strategy, at the end we obtain the different parameters that characterize the reaction, mainly conversion, selectivity, yields, and productivities. Along of this long process, we have to optimize a lot of variables that involve not only the catalytic system, but also the reaction process. Some of them are here in this slide. For us, was very important, for example, to determine the influence of the porosity of the aluminum chips. also all the variables that are involved in the preparation of the surface of the aluminum chips. Another variables that was very important was, for example, the copper thin ratio, so on with the hydrotal sites. Also, the variables that are very important in the reaction process was the temperature of the activation step, and of course all the variables that are involved in the operational process to obtain the methanol: temperature, mass flows, gas composition, and so on. As a main result of this process, we obtain a methodology to synthesize the catalyst, also a fixed composition of the multimetallic catalyst, and also an operational window in which we can operate and produce our product, in this case mainly a temperature between 200 to 150 and a ratio between hydrogen and CO2 3:4. With these operational conditions, we achieve conversions between 6 and 11% of methanol with a selectivity between 16 and 80%. Okay, another study that we performed along this project was, for example, long-term stability or on-off cycling. In this case, we can observe that the catalyst is stable over long periods of time and also is suitable to use under on-off cycling process. Another aspect that were studied was the tolerance of this catalyst to some contaminants, mainly in this case oxygen and sulfur. And we can observe that the catalyst is sensitive to the presence of oxygen, reducing the methanol production, and it's very sensitive to sulfur content. In fact, in this case, the catalyst can be totally desactivated. In the last step, with the objective to try to prove the validation of the catalyst at TRL 5, we had to modify our process to try to introduce a condenser with the objective to separate the condensed products, mainly water and methanol, and then the condensed gases recirculate again at the inlet of the reactor by means of a booster compressor. So, in this case, our best results were obtained using the conditions that you have here in this slide: pressure about 10 bar, temperature around 200 degrees, hydrogen CO2 ratio of 3, and recirculation rate of 6. With these ratio conditions, we achieve a conversion per pass of 11%, and a global conversion about 52%, and methanol selectivity around 80%. Related to the composition of our condensate, is basically a mixture of methanol and water, but in this case it has very small traces of formic acid at the ppm's level, and with a final composition of methanol about 38% in volume. So, as summarized conclusions, we can to say that we developed a novel copper-thin catalyst supported over aluminum fibers with hydrotal site. This catalyst is suitable to operate at moderate temperature and pressure. Is stable also under long-term periods of reaction and on-off cycling. it's also sensitive to the presence of sulfur and oxygen, but it has a very good performance with high methanol selectivity and good conversion per pass. That's all from my side. Thank you.
Okay, so the last part of this final event is focused on the end user applications. The first end user is EVAP. So Ashley Osge Advitu, sorry if I didn't pronounce it correctly. She will be, later we will have the opportunity to listen also Novamont, but the floor is yours, Ashley.
Thank you very much for all. Hello again, this is Dr. Asta from EVAP Turkey. I will be very, very thankful for each of the consortium members for all the efforts given by each of you. So I'm so grateful and thankful again for being a partner of this huge and nice family. Thank you very much. I know we know each other very well, but to give an idea about who we are as being EVAP for the online attendees, I would like to introduce the history of EVAP. EVAP actually founded in 1927 in Turkey, and we are operating in 4 different businesses. One of them is FMCG, oleochemical, and port management and real estate. On the other hand, we have actually 4 different facilities located in Turkey, located in Egypt and Malaysia, and will be implemented new facility in Indonesia for oleochemical industry. For oleochemistry, briefly, I can say we are one of the biggest facility and the manufacturer in all around the world. And on the other hand, we are exporting our finished product over than 100 different countries. The total amount of the employers are around, over than 3,000 for all facilities: Egypt, Malaysia, Turkey, and Indonesia altogether. We are the first R&D center for cosmetic licensed by the government for the giving license. That's why I can say we are quite honored for this to be in a first R&D center in Turkey. On the other hand, as I said, those are the facilities. The right-hand side is our Malaysia facility. Left-hand side is Turkey. The R&D center, many you have visited, as far as I remember, in 2022. So we have a role in this project for CATCO2NVERS in many different tasks, work packages. We plan to use lactic acid and also glyoxylic acid to be used in for cosmetic formulations and biocidal formulations. But because we don't have enough amount of lactic acid to be used in formulations, that's why I will give some details related with the usage of glyoxylic acid. Glyoxylic acid, we have 2 different samples in different concentrations. One is a concentrate version of the glyoxylic acid with 2.81% as weight. The other one is a dilute version of this glyoxylic acid. For shower gel, we tested in 2 different, again, concentrations, and the results are so promising for us. For pH and viscosity size, those are the first measurements, on the other side, we tested in hand creams. Hand creams also, we don't see any negative results for the first step of the first results. As expected, in adding the glycolic acid into the formulations, the pH level decreases. But somehow during the stability test, we have to follow whether there will be any change in pH, in viscosity, in odor, in color-wise. That's why we have to wait for a while, at least the result of the first month of the stability, by keeping those samples in different conditions. For example, in 5 Celsius, 25 and 40 Celsius degree, to keep as 4 and 6 months. And also we will be testing with excess of the temperature. For example, 45 and 50 Celsius degrees we have to control, and also to see whether there will be any phase separation. We are conducting some cycle tests, freeze and thaw tests. It begins minus 40 Celsius degree up to 50 Celsius degree. On the other hand, to see whether there will be a discoloration during the stability test, we are conducting some testing device to observe whether there is a change. And for sure, for cosmetic size, we plan to see the final efficacy of glycolic acid in the cosmetic formulation, because glycolic acid is very well known as a conditioning agent and also emollient type of the ingredient. So we will be testing these properties, whether it is valid for the end product, by conducting some in-use tests with different panelists, and it will the panelists will be using those products, our products, at least 8 weeks to see it really affects the, for example, this skin, improves the skin elasticity, TCT, and also removes the wrinkles or moisturizing, gives some moisturizing properties onto skin. So to receive all of the test results after performing good results in stability tests, we will be sending those tests for the other third-party laboratories to be tested, and then hopefully we will be seeing again positive feedbacks from the panelists. Whenever we receive the test, we will be sharing with the consortium members. So those are the brief test results and the studies that we performed in our R&D center. So thank you very much for your attention.
And last but not least, the second end user is Novamont, presented by Patrizio Salice. It's down. Okay.
Thank you, Pablo. I'm Patrizio Salice from Novamont. I'm very, very glad to be here. It's a pleasure to be part of the CATCO2NVERS project and have to add the possibility to test your product obtained in CATCO2NVERS. Novamont, we are the leader in the production of biochemicals and bioplastic. We are an Italian-based company, and we are based our activities on 3 pillars, which include integration of chemistry and agriculture. We are a big corporation, certified, and since 2023 we are part of the largest Universalis Group. We are an industry. We produce more than 117,000 tons per year of bioplastics. And this bioplastic is based on bio-based and biodegradable polyesters that which produce at more than 117,000 tons per year. But we produce also building blocks such as butanediol from the aerobic fermentation of glucose. And you can see where I'm going here, because of course we have some streams of CO2, very pure CO2 that can be valorized. That is why, as we will see later on, we are so involved and engaged and very pleased to be here in CATCO2NVERS. But we are also a research and development center with more than 1,000 patents. We have 13 proprietary technology, 4 of its kind, and we have almost 500 training activities done in Novamont. For us, well, we develop material, but we have always an eye up to the market, what the market is buying, what's very important. And for us, the application of our product are where the biodegradability of the product is a key factor. For example, mulch films, compostable bags for organic waste collection, food packaging, food serviceware, and bags for compostable bags for shopping bags, and all applications that are relevant. And it's been a long journey for Novamont. We started in 89, 90s, and then in these more than 30 years, we are already at the 5th generation of our bioplastics. For us, the process includes improving functionalities and performance, at the same time sustainability. Up to a certain point, sustainability means improving also the bio-based content, reducing emission, improving energy efficiency, but at the same time, we are looking at the possibility to use bio-based building block decarbonized from CCU technology in the next generation of bioplastic. What does that mean? It means that we have a clear opportunity in integrating in our existing industrial biorefinery generating CO2 some CCU technology that can convert that CO2 into high-value building blocks. And to do that, how we see CATCO2NVERS? We see CATCO2NVERS as an incredible platform technology that is able to produce bio-based building block. And for us, Novamont is particularly interested in the possibility to valorize CO2 into, for example, the dimethyl ester of furan dicarboxylic acid with the technology implemented by CSIC with the help of EasyTech and Funditech. Why is that? FDME is a monomer, is a diacid that is at the base of polyester obtained from the condensation of diacid and diols. In particular, FDME contains a furan dicarboxylic moiety, and there are already plenty of examples of different polyfuranoates that with very interesting properties that could be exploitable directly into the market. But there are some challenges. One of the challenges, for example, is that by using high temperature during esterification and polycondensations, you can see plenty of degradation activities, and basically, and we saw an example by Eva before, your polyester will turn black. So what we see, a very interesting possibility, thanks to the work done in CATCO2NVERS, was to skip completely the first esterification process, going into polycondensation, thanks to the availability of this dimethyl ester coming from furfuran and CO2, in order to reduce the thermal stress. And I believe that maybe Dulce has the original polyester here. You can see that later. We have been very, very lucky because thanks to the FDME provided by CSIC and with the reactor of EasyTech, I believe, we have indeed been able to obtain the first of its kind polyfuranoate, including FDME from CO2. Here in CATCO2NVERS, this is a real example. We have touched it yesterday, and you can see improved color thanks to less degradation, improved toughness thanks to our proprietary know-how on copolyesters of FDCA, and also we have been able to improve the hydrophobicity, moving toward higher barrier applications. So for us, it's very important that what's the outlook from Novamont, an industrial end user here. CO2 is a resource. There are, and the derivative of CO2 can be obtained can be exploited to obtain product with enhanced performances. We see that the technologies here in CATCO2NVERS, as well as in other research innovation projects related to CCU, are in the trajectory to be ready for further integration into biorefineries. And that will definitely help in implementing an even more sustainable value chain, virtuous value chain based also on the valorization of CO2. And with this, let me thank you very much.
Well, I didn't see any questions in the Q&A, but feel free to enter any questions in the chat, so maybe in the upcoming minutes we can address it. So now I would like to have a stakeholder discussion. We have an external who is joining us in a minute, but we have prepared a set of questions that maybe I can read the question, and maybe the people in charge of answering the question can come up to here. So we have been talking about the technologies, the potential uses of these technologies, but now there is a moment at the end of the European projects where we need to think how this is going to be exploitable, or what are the future applications of all this research work. And for that reason, I would like to open a stakeholder discussion. So for that, my colleague Pablo Ariño is going to be asked about what will be the market drivers in the CATCO2NVERS project. And for example, one question that comes to our mind when thinking about all these results are, which industrial sectors do you see as having the greatest potential for adopting the solutions developed in the CATCO2NVERS project? So if you... Shall I go? Yes, you can talk here.
Well, good afternoon, everyone. As Pablo was saying, my name is Pablo Ariño. I'm the exploitation manager at CATCO2NVERS, and as he was saying, we've been developing different activities regarding the exploitation task, aiming to perform a suitable strategy to move forward with the technologies that the industrial and technology partners have developed. So regarding the first question that it's highlighted in the stakeholder discussion, we highlighted like three main sectors or industries that could be very suitable to have the greater potential to adopt the CATCO2NVERS technologies. Of course, we spotted the cosmetics industry as one of the main industry that could be enhance and arrange these technologies, such as the glyoxylic acid, aiming to provide different properties that could be suitable for that industry, for the cosmetics ones. The cosmetic one is also requesting new suitable and sustainable sources to perform or to produce the chemicals, and that's one of the main industry. The other one, of course, is the plastics and packaging industry, such as Novamont presentation introduced very well, aiming to use the FDME and the lactic acid that could be suitable to develop plastic packaging solutions with barrier applications. And finally, in the long term, we also spotted the biofuels sector or industry that also can engage and can take advantage of the other technologies or chemicals that has been developed. So in a nutshell, these three main sectors could be spotted as the greater adopters for the technology solutions in CATCO2NVERS. But not only this, but as a main straightforward strategy, we have tackled them. And in the deliverable regarding the market assessment, we have developed a suitable strategy for each of them to engage and to link the technologies with the market drivers. So more or less that can
Thank you. Explain. So another important point from the exploitation point of view is the adoption drivers. And to answer this question, I would like to call EVIAP and also Movamont to come here and see if they can answer the following question, which is about what do you consider to be the main factors that will facilitate the adoption of CO2-based chemicals in your value chains? So if you can come to this stand. So please feel free to...
Thank you very much, Pablo. What's very important when it comes to CCU technologies is that there are already some possibility to integrate this technology into existing industrial plant where CO2 is being emitted, and because that could push toward obtaining a zero-emission biorefinery, for example, integrating technology and producing in situ those bio-based building blocks that are indeed useful for already existing value chains. So the market acceptance, the integration with the value chain is granted by their integration into an existing infrastructure without, for example, need of particular logistics. And for example, as CBJU says, the bio-based industry is a local business. So we have local sources, we exploit that with novel technology, and we get a product that is already useful for an existing value chain. That could be probably a very fast trajectory for the adoption of these technologies.
Thank you. This time I will answer on behalf of EVIAP. I was also in contact with the Pablos about the exploitation plan and following very in-depth stakeholder analysis inside the company, but also with customers, suppliers. When it comes to the adoption drivers, it's similar to what was mentioned by Novamont. Firstly, it's the availability and technical feasibility to source such materials locally. Considering that this will make the prices lower, but also that it's easier to achieve scalability, having enough volumes to produce in serial amounts these bio-based cosmetics that we aimed for. As you saw with the very small amounts that were received by EVIAP. You could see the two samples, but in order to have serial production that could reach to the customers, we would need not only kilograms, but maybe even tons, depending on the formulation. And then regarding the customer acceptance, I don't think that this is a very much of an issue, but more about the price that the customers would need to pay. Because if you compare current products of EVIAP that are widely available around the world, and in some developing countries they are even leading products, we need to ensure that the prices of bio-based products are competitive. And in this way, they could really be affordable by the wide public. So the customer acceptance is mostly related to the price. And then there are also factors across the value chain. So the more other cosmetic companies adopt this, the more suppliers start to produce bio-based chemicals, the easier it is going to be by different pull and push factors to get to serial production of bio-based cosmetics. I hope that this helps to answer the first question.
Thank you. Before you leave the floor, another important question that should be answered from the end user should be the barriers to market entry. So from your organization's perspective, what barrier, such as cost, regulation, customer acceptance, might limit the market entry? So shall we start with Novamont?
Thank you, Pablo. For this technology to go at TRL 9 at the commercial level, we need surely some huge investment. We need investment in Europe for European technology, and that means that we need tools to promote investment in this technology. We already have these very, very useful and great European funding projects that are putting us all together, like in CATCO2NVERS, but we need also to think, for example, as sustainable financial options. We need tools that promote investment of private company and private larger company toward adopting and upscaling at relevant scale these technologies. And that is not easy. We are suffering from the competition from countries outside Europe. The bio-based company and all the other companies producing biochemicals in Europe are, for example, paying for ETS scheme for their emission, while we can import products from China that do not pay for their emission outside. So also regulatory and that favors products that are obtained in Europe and are designed to enter sustainable value chain could be a tools to remove some of those barriers that up to now make our industry not as much as competitive as industry outside Europe. We need to look internally to what we have. We have very cool technologies. We have very great partners working together. Now it's a matter of putting those technology to the ground and build from that value chains for Europe and for our market that are protected.
I'll start with EVIAP's perspective, particularly those that we consider as not barriers. So maybe in some cases there are even incentives. Firstly, as I mentioned earlier, the customer acceptance, it's not an issue. This is the preliminary information that we have, considering different stakeholder groups around the world. Of course, if the price is acceptable. So customer acceptance, not on the bio aspects of this product, but rather the issue here would be the cost affordability as compared to conventional non-bio-based chemicals used for other cosmetic products. Regarding regulation, it is actually an incentive, and I'll tell you why it is the incentive. First, Turkey's legislation is very much favoring bio-based chemicals and production of such products, and of course the export orientation of the country. As you know, the EU, to which Turkey is in accession negotiations, is also having some incentives through the European Green Deal for all the future members that they need to comply for. So this is also giving a push for the market adoption. And maybe the last thing, which is also related not only to EVIAP's position in Turkey, but as you know, the company has manufacturing facilities in Egypt and Malaysia. This is the CBAM. As you know, many products entering the European market are going to be taxed heavily if they do not have a green impact of the production, including the products. So in this case, when you have bio-based cosmetics and the process is also getting with very much lower carbon emissions, then this becomes an incentive actually to reach to the EU market. And this is an incentive not only for EVAP in Turkey, but also EVAP in Malaysia and in Egypt to export to EU countries and other countries that favor green products. Lastly, the real solid, in some cases insurmountable barrier is related to the cost. Because when you really want to reach to a wide range of customers from different countries, customers that would not have deep pockets for expensive cosmetics, you need to make sure that you have affordable prices. And this is the big issue. And again, as Novamont mentioned, one way to overcome this barrier would be to have this locally scalable by producing or sourcing it locally. So finding these suppliers within Turkey, for example, for EVAP's case, but it could also mean as an alternative opportunity that considering EVAP's strong R&D role and that the company has its own R&D center established within the company, that it continues potentially the work started in CATCO2NVERS by establishing its own facility in the company to source these materials that could be directly integrated into the production. In both cases, whether this material is sourced in-house at EVAP or provided by a local supplier in Turkey, it would mean heavy investment into the new product development and also manufacturing facilities for that. So the main barrier here is the cost, and this is not only the cost for the final consumer, but also the cost for any company that would like to go for bio-based cosmetics production. This is the investment to start the serial production of such products. Thank you.
Thank you so much, both of you. Now I would like to introduce, we have, because outside the consortium, we wanted to also invite external people to this conference. Some of them were not able to join us face-to-face, but they are doing online. And it is the case of our Luis. Luis, I don't know if you can turn on your camera.
Sorry, we can't. We're in the car.
Okay. So maybe it would be nice if you could introduce a little bit your company, Conversions. Tell us in a few words what is your expertise, what are you do for, and then maybe I can ask you a specific question for you.
Can you hear us?
Yes.
Okay, what we mainly do is we help companies monetize their sustainability projects through our marketplace and our consultory, our registry. That's what we mainly do.
Great. So one of the questions that when visiting your company, that came to my mind was how can we add, from your perspective, obviously, how can we add value to these technologies and ensure that the corporate commitment becomes a recognized and valid asset in the carbon market?
Yeah, so here we believe that true value emerges from when we actually stop viewing sustainability as a cost and we start seeing it as a financial asset. And at Conversions, what we do is we help ensure that every technological innovation that reduces emissions goes beyond just a statistic, a sustainability statistic, and becomes a recognized technological credit in the carbon market. So that's what we believe. And what we, this way companies not only demonstrate their commitment, but they also transform into a liquid, tradable, and auditable asset, strengthening their balance sheets positioning their brand with customers and investors. And I mean, it's all about giving innovation the value it deserves, both inside and outside the market.
Great. So, Al, thank you so much. Let's see if we have time to address other question, and if not, I may have time to ask you another one, Luis. But thank you so much. Because we also want to talk about sustainability and circularity. I would like to call Dana and Nova Institute to come here. I would like to see if you could answer the following question, which is, how do you see the integration of these technologies, the ones that we have discussed during this final event meeting, into your value chains, enhancing your sustainability and circularity metrics? So Niels from Nova.
Yeah, first of all, maybe a couple of words that we are a consultancy as well, so we do not have a value chain as such, but we do see value in these kind of technologies because they enhance circularity, but that's not just at a process level where we looked at the process level circularity throughout the project, where we have recommended several strategies for the further development to enhance the circularity of each individual technology. Circularity aspects also extend way beyond the process into the value chain, where one can close material cycles, ideally through closed loop recycling solutions, but if they are not very feasible, then open loop recycling solutions may also provide options to enhance material efficiency. And in terms of sustainability, I think for many CCU technologies that are currently being developed, it's important to recognize that the one of the key aspects for the sustainability is the availability of renewable electricity. Without those available in sufficient quantities, most of these technologies are difficult to obtain emission reductions, but with these in place, that they can provide significant benefits and reduce the dependency of value chains on fossil carbon.
Thank you so much. And then I would like to call Johnson Matthew to come here to answer the following question, which is about the regulatory environment. So our question is, which regulatory frameworks and standards do you consider most relevant to ensure the market entry of these new products?
Thank you. And I'm going to go back to one of the presentations today that more or less explain what are those regulations that we need to look into. And it was Perseo's presentation where they already addressed that this is about satisfying the UK Green Deal pillars, and there's several of them. There is the EU emission trading. There is the Fit for 55, that reaching that 55 efficiency by 2030. There's a carbon border adjustment mechanism for CO2 leakage in the products and addressing them. And Johnson Matthey is based in the UK. We have separated not long ago through Brexit. It's no surprise that we got very similar regulatory frameworks around, which I forgot to say as well, in the UK for net zero, and similar emission regulation frameworks. So it's keeping an eye on them, keeping an eye on emerging technologies and wide policies and addressing them. I also want to go back to one of the previous questions, which was about CO2 valorization. And we're not an end user. We are a big supplier with over 10,000 people. And CO2 valorization is very important for us in our syngas-related technologies. And we are a committed net zero company. We're not alone. I was looking today in the database that there's over 11,000 companies all trying to address that. And when you talk about net zero, and things like CO2 valorization or carbon capture become very important for emitters and companies that still rely in fossil fuel technologies, and that transition to process decarbonization, which is key for us. And we've got two technologies on CO2 valorization, which is CO2 to methanol, which Cardiff has shown a fantastic example. In my opinion, I was discussing it with them yesterday, beyond TRL5 at this stage. And the other one that we have got is reverse water gas shift to generate syngas to then valorize into fuels through FT. Both of them demonstrate a large scale, showing how important is CO2 valorization, which is what this project is all about, and what it means for us. Probably took too much time. Thank you.
Thank you so much. The rest of the questions can be also addressed by Sustainable Innovation by us, by my colleague Pablo Ariño. The first one is regarding the investment attractiveness. We would like to ask you, I think it will be very relevant to know for our audience, what elements will make these technologies more attractive to investors?
Yeah, sure. Thank you. Yeah, moving onwards with the latest couple of questions, we would like to link them because from one side, it's quite important to get to know and to realize what does these technologies make appeal for investors to engage them into further opportunities investing in these technologies and therefore let them develop, right? So just a couple of ideas about to make them more appealing, more attractive could be to showcase that there is an interest outside, right? Not only about the customer acceptance that we have been discussing and suggesting by the end users, but also interest from the industrial partners that are interested in implement those technologies into their within their internal R&D activities, right? So it's quite relevant to showcase to the investors that industrial partners such as Novamont, EVIAP, or Leda Polymers are interested in these technologies and they are quite willing to move forward within the next steps. So that will be the first point or the first element that could make the technologies or the more appealing to investors, to showcase that there is an interest both in the public but also in the industrial partners. Also, we could tackle that in order to make them more attractive, there is a need, as said before by Patricio, to sharing the risk, right? Investors are quite willing to invest in those technologies that could gain, to let them high gain but high risk opportunities. So we should try to spot opportunities that could de-risk this investment, such as opportunities in the terms of going forward to public funding schemes, such as the EIC accelerator, that could share the risk among private investors and public schemes regarding the European Commission, for instance. And finally, to showcase that there is a clear advanced TRL roadmap. We've been very successfully developing and validating those technologies into TRL5, but we cannot stop here, but to let them know that there are different strategies moving forward to get the technologies in a higher TRL level. So that will be the three main elements to make these technologies attractive for investors.
So last but not least, and this is a question that just entered in the chat, it's regarding what are the next steps of the project, and this is quite related to the question that we had in mind, which is what steps do you see as most urgent to bring CATCO2NVERS results closer to the market in the next 3-5 years?
Yeah, perfect. Once again, once we identify how we can make attractive, we can define which are the next steps. Of course, the first one is to develop activities to move forward the TRL level, right? The technology readiness level. What does it mean? It means to not to stop at the R&D validation, but to integrate those technologies in the facilities or in the R&D activities regarding the industrial partners. So once we validate those technologies into those industry partners' value chain, we can move forward with a higher TRL level. Also, it's quite important as the next step for exploitation or for developing those technologies to define an IP and licensing strategy. So in CATCO2NVERS, we've been developing and discussing from the very beginning about what could be the most suitable strategies for exploit these technologies, and each of them has its own nature, let's say. So we can pave the way to, okay, once we have been aware about how attractive or suitable these technologies could be, it's time to let the partners discuss about how they can exploit these technologies in terms of what different schemes or strategies could arise for these projects to move forward and to define a clear strategy. And last but not least, of course, engagement among investors and policy bodies. It's quite relevant, not only it's not only needed engagement for about internal industry or R&D players within CATCO2NVERS, but we need also external contribution for different investors and policy bodies. So it's also quite needed to provide them a successful and an attractive options to let them invest and engage within those technologies. So that will be the three main steps for the CATCO2NVERS to be close to the market in the short or medium term. Thank you, Pablo.
Thank you so much for all your contribution and answering. I think I didn't see anything in the chat, but thank you so much to participate, not only the people who attended here, also the people that are attending online. If you have any kind of comments or question that you may want to ask us later, here you have our main social media channels, and also on our website you will have all the information about our contact. We have an email address, but we have also all the results published in the CATCO2NVERS website, the scientific papers, the dissemination materials, the recent updates of the project. So all the information is accessible. We try to do it as much as open access as possible, and you can find this and more on our CATCO2NVERS website. From my side, I don't have any other words or remarks. Another question that just entered was if these presentations will be available, and the answer is yes. The meeting is being recorded, so the resources, the presentations, the recording of the session will be published in the CATCO2NVERS website, and we will share probably next week or in the upcoming weeks in our social media channels. That's all from my side. Thank you to all the consortium, to all the external attendees to attend. It's been a truly pleasure to moderate the session, to collaborate with you during more than 4 years, and it's been a nice experience to share all these beautiful results with you. So thank you so much. Now, for the people that is attending physically, we have a cocktail. This is something that virtually you don't have, so it's a pity that we cannot come with your presence. But thank you so much, and I think it will be in the same place. No? Okay, it's in another place. Okay, so that's all. Thank you so much, and hope you enjoyed the session. Thank you so much.